Welcome back. We finished up with coordinate covalent bonds, and we're going to finish this section now. Most polyatomic cations and anions, there's only two cations that you have, contain covalent and coordinate covalent bonds. Therefore, compounds containing polyatomic ions have both an ionic bond and a covalent bond. Do all atoms joined in covalent bonds donate electrons to the bond? And that is, an answer is absolutely not. Some coordinate covalent bonds will share a pair of electrons from just one of the bonding atoms. Octet rule does have some exceptions, however, and these occur in a couple of positions. The octet rule cannot be satisfied with molecules whose total number of valence electrons is an odd number. So something like nitrogen. There are also molecules in which the atoms has less or more than a complete octet of electrons. So when we look at NO2, there are two possible electron dot structures, and we see that there are 17 total electrons, so someone is going to be short an electron, period, because we don't have enough pairs of electrons to get to 8 for each atom. So NO2 does exist. It is a stable molecule, but it does not obey the octet rule. And the atom that is violating the octet rule is nitrogen. Sometimes we have elements or molecules that have an expanded octet or more than 8 electrons. This can only happen when we get to the third row of the periodic table or below. So there's your third thing you need to write. And that would be expanded octets occur the third row of the periodic table and below. So in this example, sulfur it has more than 8 electrons. In fact, it has 2, 4, 6, 8, 10, 12 electrons. Definitely an expansion of the octet. And what we see is they're using d orbitals to do that. And that's why it has to be in the third row or below, because that's the first time we have d orbitals available. Are molecules that do not obey the octet necessarily unstable? And that's no, they are not. Things like NO2, sulfur hexafluoride, also very stable, and they can even be naturally occurring molecules. Bond dissociation energies, I do need you to know the definition, but I'm not going to ask you to do any calculations. So how is the strength of a covalent bond related to bond dissociation energy? Well, a large quantity of heat is released when hydrogen atoms form or come together to combine and form a hydrogen molecule. So bonded hydrogen as a molecule is more stable and has released energy versus two hydrogen atoms that are not bonded. This release of heat suggests that the product is more stable than the reactants. Covalent bond of the hydrogen molecule is so strong that it would take 435 kilojoules of energy to break it apart. So the energy required to break the bond between two covalently bonded atoms is known as bond dissociation energy. Units for this are kilojoules per mole. Large bond dissociation energies correspond to a strong covalent bond. Carbon-carbon bonds are very strong as well, and they have a bond dissociation energy of 347 kilojoules per mole. So this helps explain why proteins and DNA and all of those are very stable compounds, is because they have very strong bonds. And they are unreactive partly because the bond dissociation energy is so high. True or false? A strong covalent bond has a low bond dissociation energy. And that would be false. It should have a high bond dissociation energy. Resonance. How are resonance structures used? When I have a molecule and it has a single bond and a double bond, it's often neither of those two structures, but kind of an average of the two. So if I have a double bond on the left or on the right, they flip back and forth. And so it's really an average of those two. Because earlier chemists imagined that the electron pairs rapidly flip back and forth or resonate, and it's actually not that. It's more of that both are happening at the same time. So they called it resonance forms. It really doesn't flip back and forth. Double covalent bonds are usually shorter than single bonds, and so it's believed that the bond lengths in ozone would be unequal if it was flipping back and forth. However, experimental measurements show that the two bonds in ozone are the same length, and so it is a hybrid or a mixture, or both are happening at the same time. Two electron dot structures for ozone are examples of what are still referred to as resonance structures, and you do need to know this definition. Are structures that occur when it's possible to draw two or more valid electron dot structures that have the same number of electron pairs for a molecular ion. Chemists use resonance structures to envision the bonding in a molecule that cannot be adequately described by a single structure. There's no back and forth flipping or changing between them. We use double-headed arrows to connect them, saying that both of these are happening at the same time. Do resonance structures adequately represent actual bonding? No. Resonance structures are a way to envision the bonding and then know that both are happening at the same time. It's a mixture or an average of those resonance structures. Down to the key concepts. Covalent bonds, electron sharing occurs so that atoms obtain a configuration of a noble gas. In a coordinate covalent bond, the shared electron pair comes from a single atom. The octet rule is not satisfied in molecules with an odd number of electrons, or in molecules in which an atom has less or more than a complete octet of valence electrons. Large bond dissociation energies correspond to a strong covalent bond. Ozone is an example of bonding in atoms that have extremes represented by resonance forms. You need to know your vocab: single covalent bond, structural formula, unshared pair, double covalent bond, triple covalent bond, coordinate covalent bond, polyatomic ion, bond dissociation energy, resonance structure. And we made it to the end. Thanks for listening, and I will see you in class.